Welcome to video 2 for our 8.8, and this is where it gets a little bit more fun. When you are asked to find an interval of convergence, not only do you have to find that radius, which is what we did in video 1, basically to see how far out from that center we go, but we also have to talk about the end point of convergence. So when I talked about this right here and I told you there was more to it, well, this is the more. Not only do I have to find this interval, but I need to actually test these endpoints because I need to know if one is part of the convergence or not part of the convergence. So that's where a little bit extra fun comes into be. We're going to find that interval of convergence and we're going to test the endpoints. So each endpoint has to be tested for convergence or divergence, and then you'll be able to see, is your interval like this, or maybe do you include the A but not the B, or do you maybe do them both, okay, or something along those lines. Okay, so we need to test them individually, and the way you test them is once you find that interval, you're going to put the endpoint in for your x, and you're going to get to use all of those fun tests that we did in section 8.1 to 8.6, because once that x is gone, it goes right to what we did before. So let's get started. We're still going to start out with the ratio test because we've got powers. So we're going to do our limit as n approaches infinity. We are going to do the n plus 1 term. And then we're going to divide that by the nth term. So we're going to flip and multiply. We're going to see where we're going. Okay, so when I simplify this, your negative 1 to the n plus 1 divided by your negative 1 to the nth is just your negative 1. You have x plus 1 to the n plus 1 power, x plus 1 to the nth, so that's going to cross out and you're still going to be left with an x plus 1. You have a 2 to the n plus 1 and 2 to the nth, so you've got a 2 left over on the bottom. You don't have any n's left, so there's nothing for me to approach infinity with. So this limit is going to be convergent, or this series is going to be convergent using the ratio test when this limit is less than 1. So for convergence, I need this to be less than 1. Well, that's going to be less than 1 when, remember, the absolute value of negative 1 is just 1. So I'm going to be looking at where this is less than 1. Okay, so by the ratio test, series converges when this is true. Okay, well, using our absolute value notation, we know that that means negative 1 is less than x plus 1 divided by 2 is less than 1. If I multiply both sides by 2 and then subtract 1, I'm going to end up with negative 3 less than x less than 1. So that is my starting off point for my interval of convergence. We need to finish this interval up. So I need to test at x equals negative 3 and at x equals 1. So I am literally going to put those values in, and I'm going to write x equals negative 3. So I'm checking my point at x equals negative 3. So I'm going to go back up to my original statement here, and I'm going to look at this series when x is negative 3. Well, if I put negative 3 in here, I'm going to have negative 3 plus 1, which is negative 2, all over 2 to the nth power. Okay, well, I can rewrite that. This negative 2 to the nth power. Okay, don't, due to my space, I'm not going to write my little, no, I'm going to because I'm going to make you do it, so I'm going to do it. Toughen up. I'll move you over here. So I've got this negative 1 to the nth power. I can rewrite negative 2 to the nth power as negative 1 to the nth power times 2 to the nth power. Well, then I have that negative 1 to the nth power, negative 1 to the nth power. That's the same thing as 1 to the nth power. But now these 2 to the nth, 2 to the nth, those are going to cancel. So I literally have 1. Okay? And if you want to, you can put 1 to the nth power. Okay? But we know that's going to be 1 plus 1 plus 1. Plus 1, plus 1, plus 1. So that's going to go to infinity. Okay? So that is going to diverge. So that means when I'm writing my interval of interval of convergence, no equal to bar for Mr. x equals negative 3. Okay? So now we're going to test at x equals 1. I'm going to put 1 in for all of my x's. So I get negative 1 to the nth. When I put 1 in here, I get 1 plus 1, which is 2. Okay. So I get negative 1 to the nth power. Okay. Well, that's the same thing. You're getting negative 1, positive 1, negative 1, positive 1, negative, positive 1. It's going to diverge. So they both diverge, so that means when I do my interval of convergence, is going to be negative 3 to 1. Okay, I didn't get an equal to bar for any of them. Okay, so this doesn't narrow into a number, the other one doesn't. So we are divergent. So let's look at another one because we get some really fun examples here. Ooh, and this one is super exciting. Now, when they ask us for the interval of convergence, they like to get a little creative. So for instance, they're looking at f of x. Well, there's f of x right there. Okay, well, that's no problem. Kind of weird that they asked us like that. I'm going to start off with the ratio test because I have power. I'm going to do ratio test. Somewhere tell them you're doing the ratio test. So if you want to start off with it and then go by the ratio test, you're convergent when, that would be super. Ratio test, the n plus 1 term divided by the nth term. So we're going to flip and multiply. So then that becomes the limit as n approaches infinity of x times n over n plus 1. Now remember, you've got n plus 1, so you can't cancel that in, and that n just doesn't work that way. So when I'm looking at this, I'm looking at this limit right here. Because remember, I could rewrite this as the absolute value of x times n over n plus 1. Well, this guy right here is going to 1. So this limit is going to the absolute value of x. So that limit is going to be convergent when my limit is less than 1. So if my limit equals the absolute value of x, that means I'm looking at, oh mercy, what happened? I'm looking at where the absolute value of x is less than 1. Okay, so my start off point, okay, by ratio test, got to put that somewhere. Series converges, wow, I'm writing that really messy, converges when absolute value of x is less than 1. So if I go ahead and rewrite that, that's negative 1 x to 1. I need to test those endpoints. I'm going to make sure that I show that I am testing those endpoints. So I'm going to test x equals -1. Okay, and I'm going to put it up there. I'm checking x equals -1. So when I put that in there, I'm going to put -1 in here for the x. I get -1 n over n. I need to test to see if this series is going to be convergent or divergent. Well, it's a perfect alternating series test. So I'm going to put a little alternating test there. Okay. So I know that 1 over n plus 1 is less than or equal to 1 over n. I know the limit as n approaches infinity of 1 over n goes to 0. So therefore converges. So that means I've got an equal to bar, and I can go ahead and just put that equal to bar over here to remind myself. And notice it's in blue, so you know it was because of what we did in the blue. Now I'm going to do x equals +1 and check things out. Well, if I put a +1 in there, I get 1 to the nth power over n. That's the same thing as 1 over n. Well, that's a p series where p is equal to 1, so that means it diverges. So no equal to bar for the 1. So my interval of convergence is -1 to 1. Okay. If they ask me for the radius, my radius would be 1 because I'm going out 1 in each direction. But interval of convergence, make sure you are testing those endpoints. Okay, now I've got something a little bit exciting for you. And that is part B. Oh my goodness. So we're still dealing with the same function, but look at what they want us to do. They want us to find the interval of convergence for the integral of f of x dx. So if they want me to find the integral, I am actually going to integrate my series. How crazy is that? So we're actually going to integrate my x to the n over n and take the sigma notation of that. So if I want to integrate this guy, and notice we have that dx, so that reminds us that our x's, those powers are going up. We're not going to worry about the plus c. So when I integrate that, I'm going to have x to the n plus 1 divided by n plus 1, but I still have that n on the bottom. So this is my new series. So I'm looking at this guy. And I should have put that notation at the very beginning here. So that really should be right here and right here. Okay. So my series is now this guy. Awesome. So when they ask you to integrate, you are just adding 1 to the exponent, dividing by that same amount. Don't forget what was already there and is still there. So we're going to do the ratio test just like we did before. The limit as x of n, sorry. Too many x's and n's. Just make sure you correct yourself before you put your square of happiness around it and we'll be okay. All right, so when I do my absolute value of my n plus 1 term, this is n plus 1, so n plus 1 is going to be x to the n plus 2. And then we have n plus 1, because we had n plus 1, that next one is n plus 2. And then we have our n plus 1 over x n plus 1. So the n plus 1 term, you're literally putting n plus 1 in for all of your n's. Okay, so when I simplify that all out, really there's not a lot that cancels. The only thing that will cancel is my x plus, or my n plus 1's, those cancel. And then I do have an x left on top, so all of that will cancel and leave you with an x up there. So that will be x times n over n plus 2. Okay, so when I take that limit, all of this is going to 1. So I end up with the absolute value of x, and I'll be interested in knowing where this is less than 1 because I want to know where it's convergent. So once again, we're looking at -1 to +1. Okay. So we have to check those same points. Let me see if I can squeeze it in there. Oh, let me put it right here. I apologize, this is so messy. But maybe because it's in different colors and you're watching it unfold, you can scribe your notes a little bit nicer. When I put the -1 in here for my x, I end up with the following series. -1 to the -1 to the, oopsie, right there, n plus 1 over, and then we've got n times n plus 1. Apologize for the break. I almost tried to put it back in this original, so let's take that out of the picture so I don't look at that again, because I was like, what's going on here? No, we want to put it back up in here because we are trying to find out where the integral of f converges. So this is the function we're using to put our -1 in there. Whew, that was tricky. Okay, so when I do that, that's an alternating series because you got the -1, okay? So when I check this out, the first thing I want to check, alternating series, is to see if the n plus 1 term is smaller than or equal to the nth term. And sure enough, we passed that. Then I want to look at the limit as n approaches infinity of our 1 over n plus 1. That equals 0, so it does converge by the alternate series test. Okay, then I'm going to put that little equal to bar in there. And then I'm going to do my x equals 1. Make sure you're putting it back up in here. So I have 1 to the n plus 1 power all over n times n plus 1. So we really have, it's very, very, very close. Let me just rewrite. We have 1 over n times n plus 1. So I'm going to do a limit comparison with this guy. 1 over n squared. Okay, limit comparison with this guy. Okay. So I'm going to do my limit comparison. I'm going to take that off there. Limit, oopsie, that's a square. Okay, so I'm limit comparing it with this guy. So I'm going to take the limit as n approaches infinity of the guy I want to know divided by the guy I do know. So 1 over, and I just went ahead and multiplied that out, times n squared over 1. So I'm dividing it, so I'm flipping and multiplying. So that is going to give me 1, which is greater than 0. So I converge. Okay. So remember, limit comparison, direct comparison, if it equals a number, okay, if it equals a number, then you're doing the same thing as the other guy. So this guy converged by a p series, this guy converges. So I've got an equal to bar for both. Okay, so -1, +1. Okay. And for something else a little crazy, we can also do the derivative. Okay. So if I do the derivative, it's going to look very much like how you would find a derivative for anything else. I'm taking the derivative of the x. See, it's f prime of x, so it's with respect to x. Don't pay attention to the n's this time. The n's are going to be held constant. So drop that n down in front, subtract 1 from the exponent, divide by your n. So you took a derivative, you just use the power rule. Well, that simplifies kind of nice. That's just x to the n minus 1. Okay. So I am going to be checking this guy. So once again, I'm going to put a little box around this. So this is the series I'm checking, not that guy, okay, because they want me to find the derivative. So when they ask you for the integral, you just do the integral. Add 1 to the exponent, divide by the same amount, integrate, okay? Derivatize, or differentiating, you're going to use the power rule and all the other derivatives you know. Okay, so when I do my ratio test, okay, I've got x to the n over x to the n minus 1. So I get right to it. This is just x. So it's going to equal the absolute value of x, which is going to be convergent when it's less than 1. Okay, so by ratio test, series is convergent when the absolute value of x is less than 1. Okay, so you're taking each one. So when x equals -1, got to check that endpoint. Remember, you're going to the derivative here. Okay, so when I do that, I'm going to have my series, and I'm going to have -1 to the n minus 1. Okay, well, that's going to diverge. That's easy to see because it's just going to flip-flop back and forth. And then I'm going to pick, well, I'm not going to pick, I'm going to check at 1. That diverges as well. So my interval of convergence is my -1 to +1. No brackets anywhere. Okay. Now, what they like to do in an AP situation is they like to do what we've just done with this example 2. They like to give you a series, ask you about the original function, ask you about the integral of that series, not function, sorry, and ask you about the derivative of that series. So just because you have a power series doesn't mean they won't ask you about the integral or the derivative of it. Okay? So when they say interval of